Okay, welcome back. At the end of the last lecture, we had just derived the so-called density response function. This is the response of arbitrary physical system to a potential perturbation at some wave vector k. That potential couples to the density, and then we make a measurement later of the density and see how the system responds. Hence, density. Now, before going on, what we're going to do in this lecture is we're going to actually study this expression and find out what its properties are for various different systems of fermions, starting with a simple case of non-interacting fermions and the more complicated case of interacting fermions. But before doing so, I want to just review how it is we got to here, since it's a fairly complicated formula. So the way we did this is we started with some H Hamiltonian, which is some H naught, which is our general Hamiltonian. It could have interactions in it or anything, but we separate out from it the perturbation that we're trying to measure the response to. So there's going to be some delta H of t, which is arbitrary, with the only constraint that it is weak, and that at time minus infinity it should go to 0. So we chose to work with delta H, which is of the following form: integral dr a hat of r times phi of r comma t, where we chose this a hat to be minus e times the density, but really, and that meaning that this phi was viewed as the external potential, but we could have just as well worked with a response, a coupling of the to an external vector potential, a coupling of a current to an external vector potential, or anything we want. We can couple any operator to some external perturbation, and the same type of calculation goes through. So we'll be a little bit more general here and call this generally A. This operator generally A, and then after some time we measure some operator B of R. We want to measure that as a function of time, and we chose to measure again the density operator. So we're perturbing the system with a potential which couples to the density, perturbed with a potential that couples to the density, and then at some later time here, this is different over here, some later time we again measure the density at some position at some time. Okay. Now, more generally than what we calculated, we could generally write the response of coupling to any operator A, measuring some operator B, having coupled to any operator A, and we would write, again, making a Fourier transform first, which is what we did last time. We would write B as a function of q and omega, or the change in B as a function of q and omega, is some response function chi sub BA of q and omega times the perturbation phi external of q and omega. And in our case, we're interested in both B and A being the density, I guess up to this factor of minus E. But more generally, following exactly the same derivation, we could have derived that chi BA of q and omega is, actually, I guess we called it k. Didn't we call it k, not q? We call it k. Wave vector is k. K. Okay. Is then going to be 1 over h bar volume of the system, sum over all excited states of the system, and then you have some matrix elements: ground state, b hat of k excited state, a hat of minus k ground state, and then divided by a denominator, omega plus I epsilon minus em minus e ground state, divided by h bar, and then subtract from this the same thing with the orders reversed. m b hat of k, b hat of k ground state divided by omega plus I epsilon minus E ground state minus EM divided by H bar. So this is what we derived in the special case that both A and B are the density operator, and that gives you the density response, which is what we're going to actually be interested in. So this formula up here. So let's actually copy this formula up here because that's what we're actually going to be working with. But this Kubo formula approach is far more general. Okay, so let's put this down here again. Okay, now this formula telling us the response of the system to a perturbation is completely general. The hard part is figuring out what the energies of the system are, what the energy eigenstates of the system are, if the system is a complicated system, what the energy eigenstates are and what the eigenenergies are. So we need to figure out what these matrix elements are and what the energies are, and that's typically quite hard. So we're going to simplify our life. We'll do a simple example first. That's what we always do. So the simple example, which is already non-trivial, is non-interacting electrons. Interacting or non-interacting fermions. So the Hamiltonian H naught is just going to be the usual pi squared over 2m, and the ground state of this Hamiltonian ground state is just the Fermi C, filled Fermi C. Filled Fermi C. Gosh, okay, you can read that. Ground state is the filled Fermi C. All right, so the hard part we have to ask about is what is this matrix element up here going to? Well, we know what the eigenstates are of non-interacting fermions. We just fill up appropriate momentum states, and we know what their energies are, and so forth. But what's not so easy is figuring out what these matrix elements are. So let's think about that for a second. So first of all, we're going to need the n hat operator, and we've calculated that before in second quantized notation. We can write it this way: sum over q and sigma of c dagger k plus q comma sigma c q comma sigma. And that is just the Fourier transform of the density operator. It's the sum over sigma. Fourier transform at wave vector k of psi dagger sigma r, psi dagger sigma r. Okay. So when we played with second quantization for bosons, we derived exactly this expression for the density operator at wave vector k. So wave vector k. So what does this operator do when it is applied to the filled Fermi C? So let me draw a filled Fermi C here. It's supposed to be a circle. Okay. Oh, it's a pretty good circle. And we start with a filled Fermi C, and if we apply this density operator at wave vector k to the filled Fermi C, that takes a fermion from some arbitrary state q out of the Fermi C and puts it up here at wave vector k plus q. And in order for this to be non-zero applied to the ground state, we must have q less than kf and k plus q greater than kf. Otherwise, applying the density operator otherwise the term in the density operator gives you 0, because if you try to transfer q to some other place within the Fermi C, well, you can't do that because it's already filled. Or if you try to destroy a state that's empty above the Fermi C, that also gives you 0. So the excited states we'll be interested in then, these are the ones you can get to from the ground state by applying the density operator, are of the form c dagger k plus q sigma comma times c q sigma on the ground state, right? That those are the only states that you can, many body states you can get to by one application of the density operator on the Fermi sea, and that's the kind of matrix element we're going to need. Ground state, one application of the density operator to get us to an excited state. Okay, so the energies of these particular excited states, E sub m minus E ground state, is going, well, this is obvious what this is going to be, h bar squared k plus q squared over 2m minus h bar squared q squared over 2m, or we can write this as epsilon naught k plus q minus epsilon naught q. Okay, so that now gives us all the information we need in order to, we know what these energy differences are here, we know what these matrix elements are, we know which excited states m we can get to. So putting that all together, and also I think we use the fact that chi of k omega has to equal chi of minus k omega by rotational symmetry of the system. I think we use that as well. We come to the, we come to the final result, which requires a couple lines of algebra, which I still have to write in the notes, but it's not too hard. It's a good exercise to go through. Sum over q and sigma, and f. And f here is supposed to be the Fermi function. It's something that gives you, but we're really considering these things at zero temperature, so it's really a step function. And f here is a step function. It gives you 1 if q is less than kf and 0 otherwise, minus nf of absolute q plus k less than kf, divided by denominator h bar plus I epsilon minus epsilon naught q plus k minus epsilon naught q. So these epsilons down here are the bare energies, h bar squared k squared over 2m. Epsilon plus, this is a positive infinitesimal that we need to regularize the when we wrote things in terms of the response in time, the positive infinitesimal regularized things at time equals plus and minus infinity. So this quantity here is sometimes known as chi naught of k and omega, and it is the Lindhard response function. Lindhard, I think I spelled that right, response function, which is just the response of non-interacting electrons to or non-interacting fermions to finite frequency and finite wave vector potential being applied to it. This was calculated by Lindhard in the 1950s for the first time, which is fairly late. This index here upstairs, 0, indicates that the electrons are the fermions are non-interacting. So that means non-int. That's why you call it 0. So this is an important equation. So I'll see if I can circle it. Okay, that worked. It's nice, and we're going to work with that equation for much of this lecture. Here's what I wanted to do. So this is a Fineman diagram. I don't know exactly what. Hang on, maybe just let me clear that page. Sorry about this. Clear this page. I'll rewrite exactly the same thing in a moment. So for people who like Fineman diagrams, it's useful sometimes to rederive or rewrite this expression in terms of Fineman diagrams. And if you don't know Fineman diagrams and Green's functions technique, that's fine. It's not required at all. For really complicated calculations, it's often useful to work in diagrammatics to keep track of your perturbation series. But for us, it's easier to do things explicitly. But one reason it's useful to present the Fineman diagrams is because when you read the literature, you will often see these Fineman diagrams. It's nice to know roughly what they correspond to. So for the Fineman diagrams, so Fineman black, Fineman diagrams, actually a lot of the diagrammatic work using diagram notation for doing calculations, not in quantum mechanics but in statistical mechanics, was actually worked out, I believe, by Maria Gebhardt-Meyer around the 1940s and 1950s as well. And they got imported into the quantum mechanical world later. I think that was the order of how things were developed. Anyway, so we need the source. The source is the coupling of the potential to the density. So the source is going to be the density operator, n of k, and we know what n of k is. That's well, it'll be a sum over q, but the terms will look like c dagger of k. Well, I wrote it as k plus q before. Here, c dagger, so k plus q, c q, and we'll draw it like this. So this is something coming in at k, or being measured at k, and we have a q coming in which we destroy, and a k plus q coming out. Okay, so you destroy a q, and you're coupling to the density. You destroy a q, coupled to some external potential. The density, it corresponds to destroying the q and creating a k plus q. Then we have these straight lines, which are propagators, and they correspond to Green's functions. G of if this is labeled but with a k and an omega, this will be g of k comma omega. That's supposed to be a big omega like that. Is 1 over isn't that a watch company, Omega? Or I don't know, they have a symbol of omega, plus I epsilon sine ek minus ef. Okay, if you're not familiar with these Green's functions techniques, don't worry about it, but we can write the Lindhard response function then as a diagram, which is a single bubble, like this. So there's omega and k coming in, omega and k coming out. So the system is perturbed at omega and k. It creates a particle-hole pair. The hole is at q and omega. The hole is at k plus q, omega plus omega. Sorry, the particle is, this guy's the particle going forward. This is the hole, arrow going backwards. And then you make a measurement of density at omega and k later. And if you use the diagrammatic technique, this will then just be the sum over q integral d capital omega of g of q omega g of k plus q omega plus omega, and up to factors of 2 pi and e and things that I dropped in this rather simplified version. This gives you exactly the same Lindhard response that we derived a second ago. Okay, all right. So let's take a look at our Lindhard response function. I'm going to copy this because we're going to want it again. So copy and put it down here. Maybe just start a new page. Here we go. Put it here. Oh, come on. There. Okay, great. Okay, so chi naught. That's the Lindhard response. So let's try to understand what this Lindhard response means. Well, first thing to look at is, when is the response imaginary? When is imaginary of chi naught not equal to 0? When does it have a complex part? Well, why is it important to find out when there's an imaginary part? Well, if you remember when we defined conductivity, a real conductivity, it means that energy is dissipated, whereas an imaginary conductivity means that you have a reactive response, the out of phase response to the finite frequency perturbation, which doesn't dissipate energy. It dissipates no power whatsoever. Well, it's the same thing for this response function, except in this case, it's the imaginary part which allows energy to be absorbed, and the real part is the reactive part, which doesn't allow energy being absorbed. So this is energy absorbed. And let's find out when you have a non-zero result. Well, recall that the imaginary part of 1 over some x plus I epsilon is minus I pi delta function of x. So that means that we're going to have a imaginary part when this denominator hits 0. So imaginary part im chi naught is not equal to 0 when h bar omega equals E naught k plus q minus E naught of q, like this. Okay. Well, what is that? Actually, so we should be a little bit more careful here. That this, in order for the numerator to be non-zero, you have to have with also when also q less than kf and q plus k greater than kf, or vice versa. If they're both less than kf, then you get 1 minus 1, and that cancels. And if they're both greater than kf, then you get 0 minus 0, and that cancels also. So you have to have either one has to be greater than kf and one has to be less than kf in order to get a non-zero result. So what is this telling us? This is telling us that let's draw our Fermi C again. See if I can do this. Okay, here's our Fermi C. Oh, pretty good circle. And we have some particle at Q here, and it gets excited to K plus Q outside the Fermi surface here. And the energy that excites this is h bar omega. Okay, so this is what allows you to absorb energy when the two states separated by wave vector k have energy h bar omega, and you're perturbing the system at frequency omega, then that energy is absorbed. Okay, so it's a rather natural and physical result. And let's actually draw where in the k omega plane this is actually occurs. So I'll actually draw with the result of, so this is k, and this is omega on this side. Oops, oh, those didn't come out so well. Try it again. So this is k on this axis, and this is omega on this axis. And let's put 2kf here. And what we have is we'll have a slice coming up like this. And the slope of this line is VFQ, or VFK, yes. And then it curves upwards like this, curves upwards like this. And in this region here, the imaginary part of the response is non-zero. And outside of that region, so maybe I'll even write that, im chi naught not equal to 0 in this region. And outside of that region, the imaginary part of the response is non-zero, meaning that you cannot create any excitations with that frequency and that wave vector. Now, let's do an example so you can try to understand why it is that you have regions in this phase space where it's not possible to create excitations of a given frequency and wave vector. Let's look at the case of omega equals 0 and k greater than 2kf, somewhere out here. Okay, so here we're looking for a low energy, omega very close to 0, transition, which excites a particle greater than 2kf. Now, is that, if we look over here at our picture of our Fermi C, our Fermi C here, if we take any point under the Fermi surface, any point you want under the Fermi surface, and you excite it a distance 2kf, it is guaranteed to be outside the Fermi surface after you do that, because the radius of the Fermi surface is the diameter is 2kf, And so if I take this point below the Fermi surface and I excite it by 2kF, it's guaranteed to end up outside the Fermi surface. And in particular, if I want to make an excitation which is very low energy, the only way to make something that's very low energy is I have to get something that starts just below the Fermi surface and excite it just above the Fermi surface. So maybe from here to there, okay? From this point just below the Fermi surface to this point just above the Fermi surface, the total energy difference between those is going to be very, very small. So that's what I'm doing here when I'm making a zero frequency excitation or a low frequency excitation. I'm exciting something from just below the Fermi surface to just above the Fermi surface. But you can't do that if you need to make K, this arrow here, if you need to make K 2K larger than 2kF, because anywhere you take this guy, if you have to move it by an arrow by a distance greater than 2kF, then you're going to end up at an energy very far from the Fermi surface, and energy is going to be non-zero. So you're going to have to make an excitation, you have to be up here at finite frequency. Okay. It's also worth looking at why is it that above some finite line here with velocity of the Fermi velocity, if you're at a frequency higher than this, you can't make any excitation. So let's look at small k. And for small k, we want to make h bar omega minus epsilon k plus q minus epsilon q. We want this to be 0. But for k small, we can, well, okay, so let's write this out. H bar omega minus, I guess, h bar squared over 2m. This is k plus q squared minus q squared. These are vectors. Minus q squared equals 0. And we want k to be very small, so we can expand. So h bar omega, the k squared term, we can throw away because k is small. So for small k, throw away k squared term. The q squared terms cancel each other. We have a q squared here and a q squared here. Those cancel. And what's left is h bar over m k dot q, like this, and we want that to be 0, k dot q. I can write that as h bar omega minus h bar over m. I can write this as k q cosine theta, and I want this to equal 0, but k has to be the original k here. If the frequency is going to be small, I know the original k is going to have to be close to kf. This has to be close to the original q has to be close to kf. So q has to be close to kf. Q near kf. So I can replace this with h bar omega minus vf k cosine theta has to equal 0, and the highest, kf, vfk, I had that right, vfk cosine theta has to be equal to 0, and that means that omega cannot be greater, cosine kf, depending on the relative angle between q and k, cosine theta can go from +1 to -1, but omega has to be, h bar omega has to be less than or equal to vf times k. Okay, so that, if I back up to the picture up here, that explains why we have this edge here, above which, at frequencies above vfk, you don't get any excitations either. Okay, so it's worth now looking at a couple of, take our favorite equation here. So this is our favorite equation, or at least it's our favorite for today. We're fickle, so maybe we'll choose another favorite equation tomorrow. Physicists can be fickle. It's worth looking at some limits of this expression, really just to convince ourselves that we're not going crazy, that we have a generally correct formula that behaves the way we want it to. So the first limit I'm going to look at is omega going to 0 and small k. Okay? So let's write this. So chi k small omega equals 0. We can write this as, okay, there's minus e over v. There's our sum over q and sigma, and then I'll write this as nf of eq minus nf of eq plus k. And then the only thing that we have left in the denominator is eq minus eq plus k. Okay, so this is, so I threw away the omega piece, and I'm assuming I can get rid of the I epsilon because I'm not. We'll put it back if we need it, and we. So you'll notice that, I mean, the energy difference, because q is small, because k is small, the energy difference in the denominator is very small. And so we have a function of something which is a small difference divided by a small difference. That's the definition of a derivative. So this is a function of something minus function of something plus something divided by the difference here. Okay, so this nf here is really a step function. So we get the derivative of a step function. So I'll just rewrite that as E over volume of the system, sum over Q and sigma of a delta function, epsilon Q minus epsilon F, having taken that limit. And we can rewrite this in instead of a Q integral in terms of an energy integral. So it will be energy integral d epsilon density of states per unit volume, and then the delta function E minus EF. And so I switched here from a sum over Q to an integral over energy by using a density of states, and I end up with E times density of states to the Fermi surface. And that's exactly the static compressibility, which we compressibility of non-interacting electrons, ability, which we calculated previously. You'll recall that we had this expression, dN is E density of states to the Fermi surface times the applied potential, calculated yesterday. Okay, so that's a nice limit. We got that right. The second limit is perhaps more interesting. We'll take omega much greater than EF, a very high frequency response, and it's actually worthwhile to do this calculation in 3 different ways. So each one teaches us something. So the first way is to plug it into our favorite equation. Let's see if it will still let me write that equation. Paste. Oh, beautiful. Okay, so we're going to just take that limit and plug it into this equation here. So we want to expand, we want to treat omega as being a large parameter. So doing that, we'll expand the denominator out. Chi naught is minus E over volume, sum over Q omega. We still have the NF of EQ minus NF of EK plus Q plus K. Divided by h bar omega, that's the leading term. And then the correction terms will look like, the first correction term, 1 minus EQ plus K minus EQ divided by h bar omega, and then plus dot dot. I guess that's enough. That's all. That's actually exact still. So the leading term, so this thing in the denominator here is considered small because omega is large. So the leading term is just the 1 within brackets. But if you think about this for a second, if you treated this brackets as 1, then this sum vanishes because both terms are going to give me the same number. And this will give me the total number of particles. This will also give me the total number of particles. They have a minus sign, and the whole thing divided by h bar omega. But they'll end up canceling if this is treated as 1. So leading term vanishes. term vanishes. And the subleading term, we need to simplify things a little bit, but let's simplify things a little bit by writing E q plus k minus E k as k dot del q of epsilon q. And similarly, I guess, nf E q plus k minus nf E q will be k dot del q and f epsilon q. And then multiplying out this term to first order, we end up getting chi naught is E over V. There's this 1 over h bar omega sitting out front here. And then we have a sum over q and sigma. We get the upstairs here is, I'm going to rewrite now as k dot gradient of q and f epsilon q. And then the second term is going to be this expanded, which is now just going to be this term, and then divided by h bar omega. So I get k dot gradient q epsilon q divided by h bar omega. So, well, okay, so this h bar omega, this h bar omega comes out to here, so it's now h bar omega squared. And then this integral, this sum, I can turn into an integral, and then once it's an integral, I can integrate it by parts, so that I move the derivative from the nf onto the epsilon q, and this gives me equals minus E over volume 1 over h bar omega squared sum over q sigma nf of epsilon q, and then times k dot gradient q squared of epsilon q. This k dot gradient of q squared is actually on epsilon q. Since epsilon q here is quadratic in q, this term here is just going to give me a scalar, and the scalar it gives me is actually h bar squared k squared over 2m. And then that means that I can just do this sum. I can put brackets around this, do this sum, and get the total number of particles. And at the end of the day, what I get is minus k squared n energy over m omega squared. Okay, so this is my first attempt at calculating the response at high frequency, k squared density divided by times E over m omega squared. So it turns out that this result is actually extremely general, and we can argue that this must be the same result, This is unusual, but it's true in the high frequency limit, even for interacting electrons, even for interacting fermions. And in order to see this, okay, so we call this 2. Did we call this 2a? No, we didn't. Okay. Well, okay. We're going to do the calculation again in a different way. Okay. So we're going to go back several steps in the derivation of the Kubo formula, chi of k and omega. We had it in this sort of in this form of an integral over time, dt e to the I omega plus I epsilon t, and then the correlator n hat of k comma t, and commutator of n hat minus k 0 expectation. Okay, so this was on our way to deriving the density response function. This was one of our train stops along the way. The n hat of k comma t, well, that's just these are in the interaction representation, but we can write that out as e to the I h t over h bar n hat of k e to the minus I h t over h bar. This is well, we called it H naught, but that H naught did not necessarily mean non-interacting. So whatever this H is, it includes the interaction. It doesn't include the perturbation, it just includes the interaction. And if we're going to be interested, the key here is if we're going to be interested in high frequency, that's equivalent to thinking about small time. So high omega is small t. So expanding this expression for small t, I then get n I k comma t is n hat of k plus it over h bar, and the leading term is h commuted with n hat k. Okay, and then there will be higher order terms. So plugging this in to our commutator term here, we then get chi of k and omega is integral 0 to infinity dt e to the I omega plus I epsilon t. Then there's an it over h bar, and we have a commutator h naught n hat of k, and then that commutator is commuted with n hat of minus k. Okay? And this is a double commutator. And we've seen double commutators of a Hamiltonian with density before. And if you recall, when we wrote down before, we did this for bosons, and it's exactly the same for fermions, that h naught is p squared over 2m, the kinetic term. There might be a v of r, and there might be sum over I less than j of u ri minus rj. And the point here is that these operators, n hat, hidden in them is position operators, r. And so they commute with the v and the u and any interaction terms, any interaction with the potential, any interaction with other particles. The only part that doesn't commute is the kinetic energy term. So when we calculate the kinetic energy term, this double commutator is actually just a scalar commutator. We did this before. Is h bar squared k squared density divided by m. And then all we have to do is, so this whole double commutator expectation value up here is just a number. So this double commutator is actually just a number, and we can plug it back in up in our favorite formula up here, for the Kubo formula, do the integral, now a trivial integral, and we end up with the final result, h bar, the chi, the response at frequency k, at frequency omega and wave vector k is just there's a minus e, probably somewhere in this formula up here. I missed a, there was probably a e over volume. Sorry, way up here I lost track of the IE over h bar and the volume, so let me put this back in. Don't do that. So let me move this over. That was over here. I missed equals IE over h bar. Volume is supposed to be there. So we get minus E density k squared over m omega squared, which is exactly the same result we had when we calculated explicitly from the Lindhard calculation. And this result is sometimes known as the F-sum rule, and it dictates that the frequency at high enough, and if you go up to high enough frequency, then the response function always takes the same rule, the same form, independent of the details of the system, independent of the interaction between particles, independent of any potential that might be applied to the system as well. And sort of the intuition behind this is that if you perturb a system very quickly, in the first instant after the perturbation, the system doesn't remember that it's interacting with anything. Each particle thinks it's free, and it responds immediately to the perturbation as if it were a free particle, and only a little bit later does it remember, oh, I'm interacting with a particle that's over there as well. So that's sort of a cartoon picture. Okay, we're now going to derive exactly the same result, yet a third way, from Drude theory. So remember, Drude theory is just the classical behavior of particles in a charged particles in a electric or electromagnetic field. Here we're going to use to our advantage that omega is very, very large. It's much greater than 1 over any scattering time, so we can throw out the scattering time. We don't have to worry about scattering time at all. This is just like we did with the superconductor. We threw out the scattering time altogether, and we're going to calculate the response of the system under these circumstances. We're going to see that it gives us the same result. So we're going to need a couple pieces. The first is we're going to need current conservation, delta n dot plus the divergence of the current equals 0. So this is the particle number density, and this is the particle current density. We'll move into Fourier space. So we have I omega delta n plus I k dotted with j, or j in the parallel direction. J in the direction parallel to k is 0. So maybe I shouldn't write it as dot. So I'll just write it as, oh my gosh, no, stop. Okay, fine point here. I k j parallel. So magnitude of k and j in the direction parallel to k is probably a nice way to write it. That allows us to write the j in the direction parallel to the wave vector k is just omega over k times delta n. And then we're going to use the Drude equations of motion as well, which is Newton's equation, mv dot is minus E times the electric field. We'll also use that J is the average density times the velocity. You might say, well, shouldn't we write this as n is n bar plus delta n, because n can change as a function of position? And the answer is I don't need to do that, or I shouldn't do that, because v is already first order in small, right? And delta n is first order in small. If I try to expand this to n bar, the average density plus first order in small, I'd be keeping track of terms which are second order in small, and I only need to keep track of things that are first order in small. So average density times velocity is good enough, and that allows me to plug in to Newton's equation over here to give me m j dot, cousin of j lo or something, is minus E times the average density times the electric field, which is nice to write as E n bar times the gradient of a potential. And then we can take j dot and write it as I omega minus I omega j. And then over here on this side, we can write this as minus I k E n bar phi. So I turn the gradient into minus I k, and then I'm going to plug in this expression for j over here. So this j is then omega over k delta n, and in the end, putting all these together, I'll get delta n is minus k squared n bar E over m omega squared times phi. Exactly the same result. Okay, so you can get exactly the same result just from Drude theory. Okay, so we've studied now non-interacting electrons. We've studied completely. We know from the Lindhard equation, we know everything we need to know about non-interacting fermions and their response to an external frequency and wave vector dependent perturbation. But now we want to return to interacting electrons. So how about how to treat interacting electrons, interacting fermions? Okay, so this can get quite complicated, but there's a fairly straightforward method which which we can handle here without too much additional trouble. So we'll start by writing the response of non-interacting, q omega phi external of q and omega. And then once the system responds to the external potential, we're going to allow the possibility that there will be an induced potential at r and t, which is just given by integral d r prime v of r minus r prime of delta n of r prime and t. So in other words, that our scheme here is going to allow the system to respond as if it's non-interacting, but then once it responds, it builds up some sort of delta n, and then an additional potential is induced by the change in n, and we're going to allow the system to respond to that as well. So I guess if we go to Fourier space, Fourier, this can be written as phi induced of q and omega is just v of q, v twiddle of q, delta n of q and omega, because this up here is a convolution. So, and v here is the Fourier transform of v of r. And now the idea is to let the system respond. Let system respond with chi naught as if it's non-interacting particles, but we let it respond to chi naught to both external and induced phi. Okay, so this is the trick we're going to use. We calculated the non-interacting response. Then the non-interacting response builds up some potential, and the potential builds up some density. The density gives an induced potential, and we're going to let this system respond with this chi naught to both the external and the induced potential. Okay, so the delta n is going to be chi naught phi external plus phi induced. And phi induced, we already decided, is just v twiddle times delta n. And then we can solve this equation. Delta n equals chi naught times phi external plus v twiddle delta n to give us, I'll move delta n to the delta n, both delta n's to the other side. 1 minus chi naught v twiddle equals chi naught phi external, this, and so delta n is then chi naught over 1 minus chi naught v twiddle times phi external. And this quantity here is our total response function, the response to the external potential, and it's known as chi Rpa, is chi naught over 1 minus chi naught v twiddle, and Rpa is known as random phase approximation, and do not worry about why they call it random phase approximation. It's totally a historical accident of the people who derived it for the first time, Bowman Pines in 1952. There was some complicated calculation, whereas if you randomized over certain phases, you would get this result. No one thinks in those terms anymore. It's just the name stuck. It's equivalent to self-consistent Hartree, consistent, but in this case, time-dependent Hartree. So remember that the idea of Hartree approximation is that you recalculate the system and you treat the potential due to all the other particles, and you sort of iterate that. And this is exactly what we're doing here. The potential is built up, and you recalculate the response to the potential that is built up due to the density of the other particles. Okay, So another way to write this is to write this as chi RPA. Let's expand out this series. We can write it as chi naught plus chi naught v twiddle chi naught plus chi naught v twiddle chi naught v twiddle chi naught plus dot dot dot. In Fineman diagram language, we would write this as a bubble, like this, plus a bubble, and then the bubble is connected to another bubble by a V, so V is in between, and then we have 3 bubbles, so we get a chain of bubbles. There's a bubble chain, and so forth. And the interpretation of this bubble chain is fairly physical. You can say, well, from the first term, you're looking at the direct response of the system. In the second term, you're looking at the system responding, then it builds up some density, and the system responds to that. In the third term, the system responds, builds up some density, system responds again, builds up some density, responds again, and basically summing up this series out to infinity. Okay, good. Okay, so let's try to apply this to some interesting cases, or a particularly interesting case. So at high frequency, let's consider the case of high frequency, where we already calculated chi naught is minus e n bar k squared over m omega squared. Then we use the RPA result at high frequency, chi naught over 1 minus v twiddle chi naught RPA here. What we derive from this is that this thing diverges when when v twiddle chi naught equals 1. So let's figure out when that is. So v twiddle is just e over epsilon naught k squared, and chi naught is e n bar k squared over m omega squared. When that thing equals 1, that condition is the same as omega equals the square root of e squared n bar, density, over epsilon naught m. And this is known as the plasma oscillation. What does it mean that the response function is diverging? What it means when you have a divergent response function, it means that there's an excitation mode there. Why? If you drive something resonantly with its excitation frequency, you can drive it infinitesimally weakly and get a large response. So when you have a divergent response function, it means you have a crisp, sharp excitation mode that you're exciting. So good. If you go to a frequency much higher than the plasmon oscillation frequency, you'll recover this f-sum form again. But at lower frequencies, you discover that there is an excitation mode at this plasma oscillation frequency. Now there's a rather simple picture of what plasma oscillation actually is, and it goes kind of like this. You start with a chunk of your metal, with which we think of as having background positive charge and mobile negative charge, and then you displace the charge. Imagine displaced charge by some distance x in the x direction, and then what does it look like? Well, it looks like the following. You have your chunk of metal again, but the so x is supposed to be small. I'm going to draw it as fairly big. So this distance here is x, and we've built up the charges. So if we moved the negative charges, let's see, if we move the negative charges in I guess the negative charges are built. If we move the negative charges in this direction, then we have minus charges built up over at this end, where you push the charges to, and you have positive charges over here, where you remove the negative charges, and you're just left with the background charges. So the surface charge density of a surface is the average density times x times the charge on the electron. Okay, so this is what we've done by moving the charge, is we've actually built up a surface charge, or a capacitor, and we'll recall from Gauss's law, del dot E equals rho over epsilon naught, that the electric field is surface charge density divided by epsilon naught, and pointing perpendicular to the surface. The force on the charges is then minus E surface charge density divided by epsilon naught, which is minus n bar x, because that surface charge density is n bar x times E. So now this becomes E squared divided by epsilon naught, and we set the force to be mx double dot. I'm just using Newton's law, and examining now this equation, we realize that this is a harmonic oscillator motion with frequency n bar E squared over epsilon naught m. And it's important here to note that this mass here is the bare mass of the electron. Bare mass of the electron, mass. It's not renormalized by any interaction between the electrons, because what you're really doing is you're displacing the center of mass of all the electrons together. And if the interaction doesn't care about that, the interaction energy is going to stay exactly the same as if you move all of the electrons together. Their interaction energy, whatever it is before you moved it, is the same after you move it. Okay, so that's one result, nice result out of RPA. One can calculate the full RPA response function, chi RPA, and I'll sketch out what it looks like. Here's k, and here's omega, and we have roughly the same picture here. This is 2kf, and you have excitation modes here associated with particle hole excitations, but then up here there's an additional Sharp mode at omega plasma frequency. So in addition to this particle hole continuum, there's one Sharp mode up here at the plasma frequency, which then enters the particle hole continuum up here. Down here, again, we have frequency being Vf times Q, although maybe when we do a more detailed derivation of the response function, maybe we'll discover that Vf should go to some Vf star associated with a mass renormalization, which we'll get to in the next lecture. Okay, so the RPA approximation is sort of the first resort, sort of the simplest approximation you can come up with, which gives you a full finite frequency and finite wave vector response of a fermionic system, and an awful lot of physics is buried in it, and it's fairly simple to implement. All one has to do is calculate the non-interacting response and then divide it by 1 minus v twiddle chi naught. The static version of the RPA response is actually exactly the Thomas Fermi screening calculation that we did in last lecture. And I guess that's covered in. Maybe that's a good exercise to convince yourself of that this is really the dynamical version of Thomas Fermi screening. Okay, we'll stop there and pick up again next time.